Hello and welcome to Coffee with Caleffi. Today we are talking about some difficult balancing projects. We're going to talk about both hydronics and domestic hot water. These are all kind of reported back from the tech support lines, things that have been issues in different places that have taken us a minute to figure out, but kind of keep coming up. So that's the context of what we're doing today. I'll introduce Matt DeLuca in a minute, but he's fielding some of these phone calls that turned into the slides that we're talking about today. And we'll also go through some of the pre-submitted questions that had additional tricky topics. So to start, if you are having problems with audio, usually just log out, log back in is the best way to go. It seems like more frequently GoToWebinars changing the permissions to access your speakers and microphones and things like that. So that's usually the best way to do it. Then if you are able to submit a certificate of attendance, we'll email that right after the webinar, and then you can submit that to your authority having jurisdiction. Hydronics 36 is out. I'm going to put a couple links in the chat as I go here. It's a digital version, it's a PDF, and then the next batch of hard copies are shipping tomorrow. So if you haven't received your hard copy in the mail, look for that probably the middle of next week. So we've been doing either a plug for a charity or something like that at the beginning of Coffee with Caleffi. This one, if you've seen Bob Rohr present over the years, you've probably heard some sort of story from this book. This is a book that is kind of in the Caleffi book club and has been passed around a lot, but is really interesting and really relevant to what we do. And I think that there's a lot of rust that we're managing in hydronic systems and inside the walls of pipes. But it really puts in perspective, how important and how difficult it is to manage rust as a country. And this statistic is from 2015, but $400 billion a year just to manage rust. And that probably doesn't even really incorporate the rust that you'd have on the inside of a pipe and hydronic, steam conversion system or something like that. But is an interesting read and kind of goes through a lot of cool examples in the world of oxidation and rust that relates to us as well. So next month, we're going to talk about pressure boosting systems. So we're going to have Irfan from Grundfos. He's going to come on and talk about the modern pressure boosting applications for commercial plumbing applications and in bigger buildings, and figuring out the best way to get the pressure right. And there will be overlap for where that fits as far as our PRVs and things like that. Going back to, I think, November of last year, we did with tricky PRV application topic there. So those will kind of dovetail together because we didn't really talk about actually boosting the pressure in those applications as well. So that'll be a good one. Then next, we'll bring Matt DeLuca into the call here, and I'll put a link to the other notes and the hyperlinks that I mentioned in the first few slides there. So Matt is a technical education specialist at Caleffi. He's also one of the voices you'll hear when you call the tech support lines. So he's a plumber by trade, has worked for Caleffi and answered the phones for a while, and then is also going out into the field to do training and application specific advice for contractors and engineers in the field, and is doing a lot of the lunch and learns with us remotely too. So welcome, Matt.
Thanks, Max. How you doing?
Doing well. So we are going to cover a lot of topics here. One of the things that I wanted to mention is that these three hydronics are kind of the textbooks for what we're going to talk about. Hydronics 8 is back from 2010. This is going to be a really deep dive into probably most specifically manual balancing valves for hydronic systems, but is a really good textbook for the math and some examples to go through how to adjust and size those valves. It's superseded in some ways by Hydronics 34 just because we have more valve options like pick valves and things like that. But the earlier, deeper math would be in Hydronics 8. And then Hydronics 21 is going to cover the DHW recirc topic. So if you're looking for more examples or more background, those are good places to go next. So Matt, you get a phone call and somebody says, hey, I've got a building that's completely out of balance. I just inherited it. There are manual balancing valves everywhere. I've found some of them. How long do you think that phone call might last? Is that going to be a quick one, or are you going to be on the phone for a bit?
No, that's going to be definitely a longer one. There's a lot that goes into balancing, and Manual balancing valves obviously are typically the most common that you're going to see in the field, just because they're the cheapest up front. But um, that it's typical that they're not balanced either. They're never checked when the system is. They're just kind of installed as they're supposed to be per plan.
And I think that especially in an existing building that maybe added some more, and this could be plumbing or hydronics that added more zones or heat emitters or something. The building's not the same as it was when it was initially designed. So even if it had been balanced perfectly, which is almost, that's an aspirational thing anyway, that balancing, depends on what you define as perfect. If we're talking about, down to a 100th of a GPM, like you'll probably never get it. But at some point, those are kind of diminishing returns to get that level of accuracy. However, the goal would be that we have warm zones, that we're not walking through hot and cold office spaces, and that we don't have really long wait times for hot water. And that level of balancing is achievable with any of these valves. So we're going to talk about some pros and cons of different applications that come up and when you might want to look at one technology over another. Every one of these valve styles will work to balance a building. Some of it is, like you said, Matt, like how much time do you have? Are you able to find what the original design was, what the flow rate should be in these different parts of the building? Or are you going to be doing a lot of laps with the manometer to get back to some sort of normal there? So if somebody says, if they call you and they say, hey, I've got half of the building that was the original building, all manual balancing valves, they're adding a wing, and I'd like to go with automatic balancing valves or thermal balancing valves, what's your general advice for a mix and match approach with balancing?
A good rule of thumb is to just not mix and match. You want to stay consistent throughout the building, whatever type of balancing valve you have. If it's already all automatic and you're putting an addition on, go with more automatic. If it's already all manual, stick with that. It's just you're gonna wind up fighting yourself basically, trying to get that balance if you mix and match with those different types.
Yeah, and I think that we won't in these webinars know what your like labor rate is locally to balance it. Like if we knew that the exact US dollar or Canadian dollar per hour to do it perfectly, and we could like dispatch somebody up there to do it and say like, okay, well, it's going to cost $2,000 worth of labor to balance all these manual balancing valves. That would be good to know. That's not really something that we're ever going to be able to know over the phone. And there are some cases that like, okay, we've got 5 manual balancing valves. We don't even really know what we're trying to do anymore. Would it be more labor to try and balance out the manual balancing valves or switch to a different technology for all 5 of them? And we'll kind of walk through some examples with like examples of both, I guess, because there's not like a specific answer that we're going to say like rip out every manual balancing valve that you've ever seen, replace it with something else. That's not realistic, and that's not the best way to do it. But we'll talk about some manual balancing valve options too that can make that strategy easier. So why don't we start with a hydronics example? And let's say we have this simple system and we've got some low temperature radiant up here and we've got a fan coil down here. So if we look at these heat emitters, we might figure out with some calculations and the heat loss of the building that fan coil wants a pretty specific 3 GPM, and we want 4.5 GPM for the manifold. However, the manifold has balancing valves. So we've got all of these adjustable flow meters on the top of these manifolds. Do we need this valve, Matt? Is this manual balancing valve here important?
Or at that point, yeah, no, that one's not really doing anything. You've already got that whole return is balanced depending on which lines are open, which zones are open, and what's flowing is going to determine what's flowing through there, basically.
Yeah, and I think that so we'll walk through this a little bit, that this would be redundant the way it's drawn. If you had 4 different manifolds kind of coming off over to the left and off to the right, maybe in an enormous building, you'd want to just do like an east wing gets X number of GPM and the west wing gets a different number of GPM. but we'll kind of talk through how that makes the task of balancing everything out a lot more complicated. So in this example, let's say that we have a 3 GPM fan coil, and it wants exactly that. One of the things to note is that the delta T may be very different for those as well. So we might have a 5-degree delta T through the fan coil, and we might have a 20, 30-degree delta T through the manifold, and that's okay. I think that having balancing valves in an abundance is helpful in a sense that there's more places to control, but you can also just drive yourself a little crazy trying to adjust this, a 16th of a turn and then watching it adjust everything else here. So the 3 GPM is helpful through the fan coil. We can go through, and I think I've got a picture. This is a manual balancing valve, this quick setter. We have this for both plumbing and hydronics. You could go through and pull the pin and it will bypass water right through. Let's see if I can switch to a better laser pointer here. So it will bypass through this flow meter, and you could check it. So you could go over to that fan coil, pull it, see that it's 3 GPM, go back, not install this, and adjust all the flow meters for the manifold. We'll say that maybe this last zone here is a tower rack or something like that. What you're looking to balance, and we'll go into more description with this in the next few slides too, we want to balance these 5 kind of to each other. We want to balance the siblings to each other, and then that will move up and down as you change this balancing valve. So if you close that completely, you're going to see all of those 5 flow rates go up a little bit with the manifold. So know that without an automatic balancing valve, all of these are related to each other in a hydronic system. When the zone valve opens and closes, that flow is going somewhere else. So that is not an absolute hard number. If you pulled this pin and saw 3 GPM, but then you turned off all of the zones of the radiant, you might then pull this pin again and see 3.5 or 4, or whatever the math would work out to be. So know that manual balancing, everything open is kind of the design day balance that we're looking for. But as zones open and close, it's going to always fluctuate with the manual balancing valve. Okay, so for one of the other questions that we get, there's a lot of cool pump technology out there. When would a delta T circulator complicate things, or when would it make it more easy to hit the number in this scenario, Matt? And this is like a pretty big question, so we can kind of spend some time to walk through this. But would you go delta T exactly as drawn here?
No, I don't think so. I think that delta T is, I mean, it's, you could, I mean, it's an option on a lot of these new smart pumps. One place that you definitely do not want to use it is in conjunction with thermal balancing valves, which we're going to get into in a little bit here.
Yeah,
it's going to complicate matters a lot more.
Yeah, and I think that in this scenario too, that if the way that we described it, that this is a 5-degree delta T through the fan coil, and this is a 25-degree delta T through the manifold, what delta T is this supposed to hold? Is that going to be the right number for, it may slow down or speed up more than it needs to, depending on what's open. So if this zone valve is closed, does it know that it now needs to try and hold a 5-degree delta T? It won't know that. So one option here, I think that delta T technology is cool, but you might need to do a circulator that's a delta T circulator just for the radiant, and then do a different one for the fan coil potentially. And then you can have 2 different delta Ts to hold. But what we're going to talk about mostly is ways to balance the flow, especially in hydronics, and not the delta T, because it won't have as many inputs as you'd be able to balance out. And then we'll talk about domestic hot water as well with some examples there. Okay, so this is, Matt and I were looking through Hydronics 8. There is a very long, very good description for how you would balance a building like this. And we both had to reread it a couple times. In Hydronics 8, page 37 is where it starts. It is a handful of pages to walk through the 10 steps that you would need to balance literally just this. And it's almost something that if Matt and I were going to balance this building, we would want to be on a walkie-talkie or on our cell phones or something like that, to have somebody depend on physically where these are located to save some time as Matt's adjusting these 4 that I'm taking a look at this valve, or standing in a different point in the building, and we describe that a little bit more through hydronics. But we're talking about 10 steps just to balance this branch one group within itself before we even move on to what we call the partner valves in this example. And then we would also have to do that at the riser balancing valve level. So we're kind of starting at the smallest, at the terminal units, figuring out what the relationship between balancing valve 1, 2, 3, 4 would be. And then we're going to, once we've got that kind of relationship between the sibling set, then we need to make sure that we have the right number of GPM in relation to the, it's kind of like you're going from your hand to your wrist to your body or something like that. It's a long process. And if you went back and accidentally closed one of those balancing valves thinking it was an isolation valve or something like that, you're kind of starting over. And you may not notice a difference to the tune of 0.5 GPM, but if that one was completely turned off, you're now overflowing everything else in this entire, all 3 branches, all whatever number of balancing valves we have here. And it's a long process to do that. So if you had this exact same scenario, but now it's occupied, Matt, and all these zone valves are coming on and off as people are coming to work, if it's an office space or something like that, how do you even do this? Is this something that's achievable to get to like an A+ balance if balancing valves are associated?
Well, it's going to definitely complicate things. You want to generally kind of do this in a vacant area, or prior to actually like handing the building over, have it kind of dialed in, because it's like you said, it's not easy in the first place with an empty building. But trying to set up ladders over people's heads while they're sitting at their desk is even worse.
Even worse. And then just if all of the sun comes out and all of the south facing office spaces are nice and warm and those zone valves close, you could be sitting in front of one balancing valve with your manometer and just watch it float up and down all day. And that's a frustrating task. So I guess best recommendation would be to get a game plan together and do that after hours in some buildings, or on a Saturday or something when it's not occupied as well. But it's a lot of work. So one of the questions that, if we're looking at this building, do we need all of these partner balancing valves? Do we need all these riser balancing valves? And we'll kind of talk through that on this slide. So one option would be to just do a technology switch in your balancing valve here. And this could be for your initial set of drawings, or this could be to save a building that was really out of balance. But if we wanted to eliminate that additional work of even having to address the partner balancing valve, there is kind of a technology switch that we can make here. We talk about this a lot in Hydronics 34. So instead of doing a zone valve and doing a balancing valve, a manual balancing valve in all 4 of these spots, we could do a zone valve and an automatic balancing valve and just get that, order that to whatever GPM we need for this heat emitter. So if that's 1 GPM or 10 GPM or whatever, you could buy an automatic, and then we don't need to sub balance beyond that. We could buy an automatic balancing valve and just have one there per zone and not have to go further from that. So one of the things we were talking about before, Matt, let's say that you had fin-tube baseboard or something like that, and you were going to try and rebalance it. You could go through and adjust all these balancing valves. What would be a good way to go to just kind of retrofit with an automatic balancing valve there? How would that kind of simplify the task?
Oh yeah, I mean, if you've got fin tube, you generally know like what kind of flow rate you need through it. So you simply order up an automatic balancing valve with that flow rate on it. There's no tinkering around that pump, regardless of what that pump is doing or how many or which zones are open or not. It will provide that flow rate through it. So it takes a lot of the guesswork, a lot of the tinkering out of it, and really simplifies everything.
And 2 things to mention with that: if you're looking at fin tube baseboard specifically, you need to open it up and see how many feet of fin tube you have. You could have a 10-foot enclosure and only 6 feet of the actual fin tube. Yeah, and you're counting the 6 feet. You're not counting the amount of aluminum in the room. You want what's actually, the heat emitter is going to be the number that you would use there to go back to a chart with a fin tube baseboard manufacturer or radiator, panel radiator, or whatever you want. The actual space that's going to be radiating the heat is what you're counting. One thing that we talked about ahead of time with this too is that did we make thermal actuator zone valves? Do you want to talk about if this was like a wooden enclosure around a heat emitter, and we'll say it's a panel radiator or something like that they're trying to protect in a lobby, which zone valve would you rather put into an enclosure like that, and why? Do you want to kind of walk through that?
Yeah, excuse me, great point. Yeah, you definitely want to go with a more traditional like paddle style zone valve in that scenario. Thermal actuators operate by, you run a current into them, they melt some wax. Due to that heat resistance inside there, they pop open. If you've got them enclosed in that radiator or that cabinet, that baseboard, it's never going to cool down enough to solidify and close off. So once that opens, it's just going to stay open. So you want to make sure that if you are using a thermal actuator, that you pay attention to the ambient temperature that it wants to be at.
Yeah, and that we've had some cases where just it will never be less than 110 degrees in that like wooden aesthetic enclosure that's, to keep people from bumping the luggage cart into the radiator or whatever. But you need to pay attention to not have ghost flow issues, or that one's not really ghost flow as much as it will never close. In some cases, if it's hot in a hot enclosure, the wax actuator is not the right valve for that, or it might need to be moved into the hallway or something, and instead of being in that hot enclosure if you still wanted to use that technology. So then the next thing is like, well, what if we wanted to actually simplify this even further? So instead of doing a balancing valve and a separate zone valve, this is where a pressure independent control valve comes into play. And we'll talk about the difference between these technologies a little bit more on the next slide. Pressure independent control valves can take a modulating input. You can send that a 0 to 10 signal, and that is like the premium way to just really cruise control the amount of BTUs into a space. And in conjunction with a really well constructed building automation system, you could get down to 10 BTUs. That's probably an exaggeration, but you can get right down to like the exact number of BTUs you need to match the heat loss in a space, versus kind of overshooting, undershooting like you would just open and close with a zone valve. However, you can also control pressure independent control valves with just an open close. But the cool thing about this setup is that you can take the balancing valve and zone valve and really combine them. So it's like an automatic balancing valve plus a zone valve is what the pick valve will be. So to back up a little bit, we'll start with the pressure independent balancing valve. Kind of the generic name for these in the market would be an automatic balancing valve. This is going to be something that you pick, like Matt said, you pick a flow rate. As the pressure developed changes, it's going to change the size of the orifice. So you can see as the pressure is low, the spring is all the way extended. As the pressure builds from the circulator, and maybe this is a single speed pump, just as more zones close, so more of that flow is funneled through the one remaining open zone, it's going to compress that spring, and it's going to change the size of the orifice, which is kind of like a half hourglass shape that we build into the cartridge that we'll show, I think, in one of the next slides here, a little bit of a better cutaway of that. So this is available for domestic hot water or hydronics. The nice thing here is you're not going back to adjust anything. We'll show you what could happen if you do need to change actual cartridge, but these are adjusting to maintain the flow rate that you pre-selected, and that can be super helpful if we're talking about a fan coil or something. Like, nothing's changing here. We're not going to go back and like balance more flow through a radiant manifold as we add zones and we add a towel rack or something like that that's on the like 6th port that wasn't used in the past, or something that we might need to adjust everything. This is going to really simplify that task, and then takes that the manual balancing valve and the sub manual balancing valves at the branch level and at the riser level out of the equation. You just need one of those. You don't need to do multiples. So then for a pick valve, and we have some of these in the building in Milwaukee where Matt's sitting right now too, we're really adding a zone valve to that. So do you want to talk about kind of what you could do with this? You take this green cap off and you put on the on-off actuator. What does that kind of effectively give you there in a smaller package?
Yeah, exactly. That's exactly combining a zone valve with an automatic balancing valve. So it even has some adjustment within it. So once you know the range that you're looking to flow through there, you can dial it in prior to even, connecting flow to it. And then, like you said, you unscrew that green cap, which at this point right here is just kind of a manual on-off zone valve. But you take that off, you replace that with either a thermoelectric or 0 to 10 volt actuator, and all of a sudden now it's both a zone valve and a balancing valve.
And one of the things that even in my own mind, I've always pictured a PIC valve as kind of the premium way to do zoning and balancing. But you had mentioned too, I mean, it's half the amount of brass roughly, and it's only 2 press connections to do your zone valve and your balancing valve. And you can test it if you needed to for whatever, if you needed to do a balancing report, or your state, like the state of Oregon, requires a different balancing contractor to come verify that you did the job right. You still have those ports. You wouldn't need to use them. You can just kind of pick the right cartridge, set it ahead of time, and put the actuator on like Matt's describing. But in a way, it's not as like complicated or as premium as it sounds. Requires a little bit more planning. We're not going to have a PIC valve on the shelf at all the wholesalers in North America where you might find a zone valve everywhere. A standard like paddle style, like our Z1 actuator, but it could be well worth the labor savings to combine those and the space savings. So
yeah, definitely. I mean, space is absolutely a premium on jobs too, and it's not getting you're not getting more space usually to work with. So if you're any components that you can combine, you're better off.
Yeah, so I think that it's something to consider, and even something as we've talked about zoning for years. It'll be 25 years in North America next year. The zone valve, the Z1 zone valve, was really one of our first products. And that was something that Mike Schreiner, our COO, that was kind of his brainchild from his previous experience as well. So we've had those paddle style balance, or those paddle style zone valves, as kind of our number one technology for a really long time. They're still a great fit in many places, but I think that we've maybe even overlooked some of the PIC valve applications just from a labor savings standpoint. That there are some applications that we've done internationally that are big, tall towers in Dubai that they like the PIC valve because they want just absolute premium engineering, and it's super intense cooling loads and things like that. So they like the PIC valve just because it's the most accurate. But I think we maybe are overlooking some of the on-off applications there. Okay, so we're going to switch over to a domestic hot water scenario, and then we've got thermal balancing valves here. So what about these locations, Matt? Do we need to, and we could say maybe this is like the east and the west wing of a bigger building, do we need to have additional thermal balancing valves at these locations that would kind of gather the 2 thermal balancing valves just ahead of them?
No, those 2 that you have on there already are going to be doing all the driving. They'll open and close as needed, and whatever flow is flowing through there will make its way back to the circulator. You don't have to balance it twice, basically.
Yeah, and I think that we'll cover this in another example in a little bit more detail too. But if you set this at both of these at 120 degrees and this one at 120 degrees, to maintain 120, these would open more, and then you could kind of fall out of balance with all of these in order to balance the full gather of both of them the way I have it drawn. So in this scenario, you've got 3 balancing valves and you ended up really only having 1 that's kind of just going to find a balance for the path of least resistance back to the mechanical room. So you've kind of reduced the effectiveness of the riser level balancing valves that I show here by adding another one here that may it may act almost more like a delta T circulator at that point, that you don't have as many decision points. That's what we like about the thermal balancing valves. If we had 10 risers in this building, we have 10 different valves that are going to react to what they need in that riser dynamically, depending on how many people are using the fixtures and if the floor is unoccupied, or if everybody is taking a shower in a hotel at the same time at 5 p.m. or whatever. They'll react to that. So we want to let them do that on the smaller branch level. So then we'll talk a little bit more about the how we would adjust these in the next set. But again, to kind of come back to this, and you mentioned this a little bit, if we have thermal balancing valves, we'll just say these 2, I can take these back off. would a delta T circulator be helpful here, or what would you want to kind of consider as far as the setting that you would have there?
No, well, if you've got a delta T option on a pump, you've got a smart pump that's got a delta P mode as well. And that's really what you're going to want to be using if you've got thermal balancing valves. It'll sense that pressure change as they open and close, and it'll adapt as it needs to in order to provide enough flow through them. If you've got, that delta T mode set on that pump, and as well as thermal balancing valves, you've just got too many components trying to make the same decision.
Yeah, and I think that I don't want to, in this webinar, I don't want to knock delta T circulator programming, because I think that there are really good applications for it. And if I had a recirc loop in the house that we live in, that might be a perfect fit for it, because I don't have a bunch of thermal balancing valves in my house. It would act as the thermal balancing valve to maintain a delta T there. And if everything's warm, it's going to slow way down and everybody wins there. I think that what we want to avoid with the delta T circulator in conjunction with thermal balancing valves is if this first riser comes back warm, because there's hot water being pulled past all these fixtures, it could slow down and the rest of the building could still be cold. So the pressure, then the thermostators are starting to open because there's thermal balancing valves trying to maintain a temperature, and the delta T circulator is like, I'm fine, I'm warm, so everybody else is going to have to deal with it. Where what Matt's describing, if the pressure that the circulator is trying to overcome drops, it's going to speed up to maintain that, and that's kind of what we want to react to all of these thermal balancing valves opening as they cool. We need the pump to work a little bit harder to get warm water out to them, and then they'll kind of react to that as they warm and start to close again. Okay, so then one thing, this was a pre-submitted question, as far as sizing these thermal balancing valves. One thing that's important to look at, the question was about pump sizing and how it relates to thermal balancing valves, because it is a dynamic C sub V. We actually publish a line on the flow curves that's the design C sub V. And that's a good one to look at, because you could look at the chart for a manual balancing valve or an automatic balancing valve and get a C sub V at different points or whatever. This is going to fluctuate as it heats and cools. So this black line is C sub V. That's a little bit hard to see. C sub V design is a good one to work from for your circulator sizing, to make sure that you have enough circulator to overcome that, the friction of the balancing valve. Okay, so for the next one, let's talk about automatic balancing valves. And we had a question, do you need shutoff valves prior to or after the Flowmatic? Yeah, every time that you can have a balancing valve with isolation valves on either side of it is like absolute best case scenario. And we'll go through a couple examples of the kits that you can put together too, to show you how to do that. Okay, so here's something that I'd like to point out, that let's say that we had a engineered building, and this is what it looks like. It's all pretty straightforward. We've selected half a GPM for the recirc line coming back. We have a half a GPM cartridge in these automatic balancing valves. But then the as-builts now have a completely different set of fixtures. We've got this huge tub. We have a bunch of structural things to work around. We have now some like telecommunications lines that we have to go around in the chase. We have 50%, 100% more fittings in this system than we thought. There was a new sink added. There's a pinhole leak somewhere. The as-builts rarely ever match the plans unless you've been to some job sites, Matt, that the plans are just like an absolutely perfect representation of what the building is 20 years later. Has that
I don't think I've ever been on a job where the original plan matched the as-built, to be honest with you.
Yeah, so we're reacting to this. So now maybe that first riser is exactly as we calculated it, still half GPM, but what do we need now for an automatic balancing valve for this riser here that's going to have a different pressure drop? It's going to have a different delta T than we had planned for. Now what? Are we in trouble here, Matt, or are we able to save the balance of this building if we can figure out what flow rate we would want here?
It's as easy as taking that balancing valve out of the unions and replacing that cartridge. It's they're available. If you if the plans say one thing and it winds up not being the exact amount of flow that you need through that, we offer replacements, and it's really that easy.
Yeah, and we'll kind of walk through the process with the next couple slides here. One question that we wanted to ask you as we were rehearsing here, where did you get this half GPM number? For anybody on the call, the half GPM is kind of like the magic DHW riser flow rate. Where did you find that number? You can type
that seems to be kind of the rubber stamp that's on most plans, to be honest with you.
Yeah, and like, it's in a lot of places. It's in, you know, all of the trade organizations and things like that. You'll find that half GPM number as a starting point in a lot of places, with, you know, reasons that you would calculate it higher or lower. But it seems like what we see is like half GPM unless proven wrong, or unless, you know.
I think one good reason would be that it's a safe velocity. If you've got a half-inch return line, half a GPM is perfectly fine in there. And if you need more, we'll cross that bridge when we get there.
Yeah, and I think that's, you know, from a velocity standpoint, that's a good speed limit to work with. But it doesn't really, you know, half GPM is not going to be a fit for both of these anymore. And, you know, calculating that is more work than, you know, hoping that it'll work, even if the plans change. So let's say in this scenario that we've got automatic balancing valves. This is now cold. This last return is much colder than we expected. You know, first of all, how would we know that? One of the nice things that you can add is a tailpiece that has a temperature. So we do a lot of balancing by trying to figure out the flow rate. What are we actually like trying to maintain in a domestic hot water system, Matt? When is everybody happy? Is it at a flow rate or something else?
Oh, yeah, ultimately it's just temperature. You just want hot water when you open that tap.
So this could be any combination of flow rates and cartridges and things like that. But if we desire the temperature to be 120 degrees at the end of this recirc line, we can take a look at this temperature gauge and see if that's right. So in this scenario, you might have exactly 120 degrees here, and you look at this and it's 105, and people are complaining about longer wait times for hot water. We now can visually take a look at that and see if we're where we're supposed to be. So it doesn't really matter if this is a half GPM cartridge or if it's been changed. If the desired result is to have 120 degrees Fahrenheit at the end of this riser, we may need to swap a part here. So as Matt mentioned, ideally we order all of these exactly as they're supposed to go in. We have a little arrow there that it's a little bit hard to see. The tailpiece is going to be on the downstream side here. So from the top to the bottom, you can crack this open. You can put in a new cartridge. We will, if this comes up, send a new cartridge and a new sticker, which is important, because if you swap a half GPM cartridge for a 1 GPM cartridge and then that doesn't work, you're going to be especially frustrated trying to figure out what's going on there. If you're troubleshooting something that you think is half GPM and it's actually 1, that will be tricky. So we also have these tail pieces that will go to an isolation valve. So a stem extension, if you have really thick insulation requirements for your jurisdiction or just a standard, depending on what you're looking for. And those will fit on both sides of these valves to kind of make whatever kit is useful for your application. And we love to hear that there's a isolation valve if we're trying to swap a cartridge or something like that, just so we're not getting more, you know, water out of that system than just a half a cup that would be in the valve or something like that, probably even smaller than that. What else would you add about this when this has come up in the past, Matt, as far as walking somebody through switching a cartridge here?
I mean, this is where isolation valves, you know, always come in handy. You don't have to drain down the whole system if you've got valves on either side of it. I mean, you can see the posi stop O-rings that we've got there that are foolproof. So there's no fiber washer that you have to have on hand. If you do pop that out of the unions, replace that, just pop it right back in and crank it back, and you're right back in business.
As you were saying that, Matt, I got a call from legal. They said foolproof is not a term we can use anymore. There's always a trickier way to do that. But I think that that is a very good point, because as you swap the cartridge, it can be frustrating if you have to find like a new version of whatever sealing here. these posi-stop O-rings go to a metal-to-metal stop, and you can reuse them. So if you did have to crack this open and put it back together, it's going to make that task easier. You don't have to go back and figure out what the original part number was to get the gasket to match that. And it makes this task a little bit easier to put back together because you're not adding any new parts to this. If you had to take it apart and clean it out, as is another example, that you're not, every time you're cleaning it, you're not looking for new parts to put it back together. Okay. So in this case, when we kind of talked through parts of this already, but we had the as-builts are not matching the plans. We thought we had 120 year, and now we have a different temperature here. We can easily verify that with the temperature gauge and figure out how we get back to the right temperature there. We are still taking, if it were a manual balancing valve, we'd be adjusting it to try and find the right temperature. Having the temperature gauge is really useful for the commissioning here, to put in a new cartridge, and then you wait 5 minutes and see if it got up to temperature. It's kind of the retrofit project here. But same thing, you could add all sorts of new stuff, and you would have the option with the automatic balancing valves to go back and change cartridge if you need to. Again, best case scenario, all these are ordered ahead of time, and somebody puts blue painter's tape on all of them to say this is going on riser 4 on the 4th floor, and make sure you point it in the right direction or whatever. But we can help out if an automatic balancing valve that's the wrong cartridge is not the easiest thing to do, as far as the other valves that we're talking about, the manual and the thermal, you'd have on site just your hand to be able to adjust it, where we are going to be part swapping a little bit here. So you don't want to take a wild guess at what the automatic balancing valve flow rate would be, but if you did have a zone that you needed more, you could go with that. So another option, instead of automatic balancing valves, would be a thermal balancing valve. So in this scenario, Matt, you're supposed to have 120 at all of the different ends of the risers, and you don't anymore with the thermal balancing valve. So what do we do next? How do you know there's a problem, and then what do we react to there?
Well, you know that there's a problem if the hot water is not there on demand or very quickly after you open up that faucet. And then instead of having to swap any kind of cartridge or anything like that, it's literally as easy as walking up to it, giving it a little 5-degree crank, and letting that sit for a couple of minutes, checking it out. And it's that easy to adjust and modify and go from there.
And I think that one of the helpful parts here is the recommissioning of this. Doesn't mean you need to get your manometer out and walk to every part of the building. You turn it up 5 degrees, and then you just wait and you see if it increases the temperature on the gauge there. That is a dry well. If you did have a fancy building automation system and you wanted to put like a thermistor in that, you could do that too. So that depends, it's easiest to just look at an analog gauge and figure out what you need. But if you did hook all these sensors up to a computer somewhere and monitor that, like, hey, for some reason, riser number 6 is always cold, you could go and use that as your basis of information to turn it up a little bit. What Matt said about just turning it up 5 degrees is important, and we're going to kind of cover that in the next one. That the cool thing about the thermal balancing valves is if you turn this one up to 125 and then give it a second, it doesn't change what the other valves are doing. So they are going to react, and they're going to move to somewhere else on their curve to open and close that valve accordingly to maintain 120. So you don't have to go back and set all of them to a different temperature. And that's kind of a tech support call that Matt will walk us through here. Best of intentions will kind of cover what would happen if you just turn them all up. So you've got one riser that's not keeping temperature, and then I went through and I turned everything up. What happens here, Matt, with these temperatures if that's the case?
Yeah, I mean, obviously they're never going to close if you've got them set above the temperature that you're even sending out to the field. But I had a call with a gentleman a couple of years ago now at this point, but he wanted to try out this new technology, these new thermostats that we had. Had I think 4 risers, 4 recirc loops, all coming back to this mechanical room. Loved the idea, loved the how it looked and everything like that. Put them in, and then gave me a call about a week later after he put them in and said, "Hey, what's going on? None of these things are working." After a couple of questions back and forth, well, what temperature do you have them set to? And what temperature do you have going out to the field, out to the rest of the house? turns out he had them all, cranked up about 20 degrees above any temperature that they would ever achieve. So they're all wide open. Those first 2 loops were maintaining because that's the path of least resistance, but the last 2 were not getting any kind of flow at all. After he, he didn't have to get wet. He didn't have to get into the piping or anything like that. Just a quick little adjustment on the knob, and called me back 15 minutes later and said, "Wow, these things are great. I can't believe how well they're working."
Yeah, and that's kind of the fun part of the thermal balancing valves. In some cases you could, if these were all manuals or automatics, either start adjusting or start changing cartridges if you wanted to. But just that 5-degree change, or you're going back down to 120, and then maybe this one does require 125, you're going to see those results right away. It's going to figure it out like as you're standing there. And we had a hotel in New Jersey at one point that had been like a decade that they had been trying to get the building into balance, and over different tenures of different people, and all best of intentions and best attempts, but trying to even find all the manual balancing valves, and then just kind of manual adjustments of ball valves hidden behind sheetrock and stuff like that is hard to do, where they were able to retrofit the thermosetters in and kind of right the ship quickly there. So only adjust the cold loops if you are troubleshooting beyond there. Okay, then let's talk about, this one comes up quite a bit too, as far as gathering the returns for the DHW. This was another tech support call. If you want to kind of talk to us about what you had with this project, and this is one of many times we've had this conversation, but give us the story with this one, Matt.
Yeah, absolutely. So if you can imagine, this is kind of a plan view of a large apartment complex. Each of those lines is coming from below, where it's 4 stories stacked on top of each other. All this is 1-inch copper coming up, coming over, and then coming back down to the bottom of the picture here. No balancing valves anywhere in the building. So if you've got 48 units on the left-hand side, 48 units on the right-hand side, those first 2 branches on the left and the right were getting some sort of flow, and so they were not complaining, but now everybody else is. So if you go back in, and even if you kind of take like an automatic balancing valve, you put a 1 GPM balancing valve on each of those branches, you're looking at 12 GPM on the left, 12 GPM on the right. So if you see where they kind of come together down at the bottom there, 12 GPM in 1-inch copper, you're already at 4.9 feet per second. Now, good, what the Copper Manufacturers Association recommends is 2 to 3 GPM on a constant hot recirculation loop. So you want to definitely try and stay within there, or you will get some very good pitting and really wear away the inside of that pipe with some corrosion actually is what it's called. So in order to avoid that, yeah, there's a couple of really good pictures that I found online recently that, I mean, you can really see that copper is just getting pitted out. In order to avoid that, what you do is you can increase the pipe size. So at where that top 1-inch question mark arrow is pointing, if you bump that up to 1.5 inches, now all of a sudden that same 12 GPM is already down to 2.2 GPM. So you're right within that allotted speed limit. Where those 2 branches come together, so now the left and the right, since they're kind of mirror images, you've got 12 GPM coming together. 12 GPM in 1.5 inches is back up to 4.4, so that you're already, that's back above what's recommended. So if you bump that up to 2-inch piping, that drops that down to just under 2.5 GPM, or I'm sorry, feet per second. So that will absolutely save your piping from looking like that.
One thing that has come up in the past too is that either installers or engineers will say, wait a second, we're going to go with a little bit thicker wall copper here. Is that, if you had just gone with a different letter of copper wall thickness here, what does that do for you?
It'll buy you some time, basically.
Yeah.
That's about it. It's still the inside of that piping looks like that, and it's going to work its way out. There's actually a job that I was involved with for years when I was out in the field. That's not too far from our offices here. That I was out there every couple of months because what they would do, they didn't have balancing valves anywhere in the building, kind of just like this. And the way, one way that well, a lot of times people try to cure that is putting a bigger pump in, and that will get that flow out a little bit further. But you're also obviously that velocity through that piping is increasing greatly. So I would go out there, I would cut into that copper, and if anybody's ever used a close quarter cutters that kind of wraps around the piping, I would put it on there and it would crush like it was made out of tin foil at some point. So it was pretty crazy. But yeah, we were there for months and months and months, just cutting out the next pinhole and replacing it with PEX and the next pinhole.
Well, and even that's a good thing to mention too, because there's no wrong piping material there. But if you did start with 3/4 inch copper or whatever, and you went back in with 3/4 inch PEX because it's easier to make the repair, you've also changed the pressure drop through that loop a little bit, because the ID is going to be a little bit smaller with PEX. So that's something to keep in mind too, that if you had 3/4 inch copper that you're replacing a bunch of pinholes and go back in with 3/4 inch PEX, it's going to make that job easier to kind of snake it through the wall potentially. But you'll need to pay attention to that could kind of like, I'll go back, that could change almost, not physically longer, but more pressure drop, as if it were more fittings with the copper to go around everywhere. And is something that as you mentioned, the wall thickness is going to buy you a little bit of time. In the example that you gave of increasing the size of the circulator, we didn't get to it today just because we had enough slides for the time. There's a whole webinar that we did with Mark Etherton about a building in Colorado that they had done kind of that as, all best of intentions. The maintenance team had, in a bigger building, replaced the circulator, 1 size bigger, 2 size bigger, 4 size bigger, and they did force more flow into the building, but what they were doing is just screaming through the path of least resistance riser. So then they did not get warm water out to the extremities of the building, to the most hydraulically remote areas, but they were just completely Swiss cheesing that first unbalanced riser, so that there's no wall thickness of copper that's going to keep up with 4 times the DHW circulator. Seems like a good path to go to make that circulator bigger if you're thinking about it in a hydronic sense. We don't have enough flow over here. We probably don't have enough pump, but usually the culprit is the balance, not that the pump isn't big enough. A well-balanced building, especially with thermal balancing valves, might be a 10% at the flow rate that you had planned for, because we're kind of planning for that, almost like hydronics, the design day recirc needed to get a cold building warm enough to open any faucet in the building and get hot water in a short amount of time. But an occupied building is going to be naturally drawing hot water through. So to maintain the temperature that you're looking for, you're not going to need as much flow as that half GPM design. So you could be 1/8 of a GPM or something much smaller in an occupied building.
One thing to keep in mind too, if you are going to be retrofitting, cutting out pinhole copper and replacing it with PEX, is that velocity actually goes down. A lot of PEX manufacturers recommend 2 feet per second maximum. So just something to keep in mind when sizing and replacing them.
Yeah, so I would say if anybody on the call is in a scenario where they're replacing a bunch of pinholes, I would say PEX is a good way to go as far as the ease of fixing it and patching it in a building, so you're not soldering in a wall in an occupied building. And there are plenty of talented plumbers that can make that happen. It's going to be a little bit longer work versus just using PEX to repair it, but also definitely look at the ECM circulator option as well. So slowing down, like Matt's saying, to that 2 feet per second. And even the copper people are saying that above 140 degrees. That's not polymer pipe specific, that above 140 degrees, the 5 feet per second is going to be too fast, or can just be a bigger scale issue as well. When the water temperature is that hot, you're going to get more minerals on the inside of the pipe. On the exact opposite side of this spectrum, that it's going to just scale down to an 1/8 inch copper pipe after a while if the water's really hot and really hard. So the opposite, where your close quarters pipe cutter is going to take a while to get the gobstopper in that scenario if you have, a pound of calcium that's built up on the inside of the pipe.
That's when you grab the bandsaw.
Yeah, that's when you get the sawzall out. So the last example that we'll talk about, ghost flow, is one of the topics that we mentioned, and we're going to go back to a hydronics example here. So one of the things that comes up quite a bit, there are many hydro separators on the market now. This was 20 years ago. This was kind of a newer technology. It's become so much more widely accepted as a way to separate the flow rates between the boiler and the system side. One of the ways to become more cost competitive in this market is to make this device physically smaller. So the golden ratio that we're looking for a hydro separator is a 3-to-1 ratio of the barrel diameter to the incoming pipe. So if this is 1-inch pipe, we've got a 3-inch barrel. We could make this less expensive by doing a 2-inch or a 1.5-inch barrel, but you could fall out of your primary secondary compliance in that scenario. So let's say that we turned off both of these circulators. You turned off the power to that relay box or whatever. This circulator is still going. So we've got the boiler into some sort of service mode to do a combustion check or something like that. We only have the circulator on for the boiler. It's going full speed. If you had a balancing valve right here and you pulled the pin of this quick setter and you saw 3 GPM, you are not hydraulically separated. And that's kind of one way to see the symptom. We should not have any flow there. So that is a ghost flow scenario, that if one of these zones was closed or the other one, and we have more flow, if we're not actually primary, secondary completely separated there, that this circulator is influencing flow across the device here. It could be closely spaced tees that are too small or too far apart, or it could be a hydro separator that is physically too small for the flow rate that we're talking about. But if we see some sort of flow there, we don't have primary, secondary piping, you could cut in and put in with press connections a flow device like this quick setter here that you'd pull the pin and see the flow rate. You can also just take a look with a thermal camera. It's probably the best place to start. I think that technology has gotten so much less expensive. I remember that John Siegenthaler at one point, to do some of the pictures that he did for the Modern Hydronic Heating book, he had to rent the camera that was like a $50,000 camera and sign some, you're not going to break this, right? Like, you know that this is a $50,000 thermal camera that's, so much worse than even the resolution of your phone camera now. That has come down to like a couple $100. You can get a thermal camera that would give you an idea, without even putting in a flow device here, that if these circulators are off, this one's on, and you're seeing this pipe heat up, it shouldn't. You should not have flow over there, and that'd be a good indication that you have some sort of influence of this circulator across the primary, secondary device, that's not working for some reason. Could be closely spaced tees that there's a ball valve in between. We've seen that before too, where there is some pressure drop with that ball valve that is not the same, even at a full port, as a straight length of pipe in between there, and you can start to influence flow across. So that could be a cause of flow where you don't want it in a system. What about the C sub V of the zone valve? I think that at most wholesale houses, you're going to find a lot of 7.5 C sub Vs on the shelf. That's a pretty common one. When would you start looking at the size of the orifice in a zone valve, Matt, if you had some ghost flow issues?
Yeah, I mean, if that pump is powerful enough that it's blowing that 7.5 CV valve open as it's closed, then you start looking at smaller orifices, smaller C sub V valve bodies. That would help in that. That gives them a higher close-off pressure rating.
Yeah, so then if you went, and this is going to be more pressure drop, but also it's going to give you the ability to have a higher pressure close off. It's just a smaller orifice to, the paddle is going to fight it closed and be able to hold it closed. Where if you oversized your pump and have the bigger orifice with this 7.5 C sub V, that could be a ghost flow scenario, that this valve is closed, there's no power to it, but you take your thermal camera and you see that there's still like a flow of hot water, it's open and it's red hot, the same way that the zone next to it is that it's open. It could just be held open by an oversized circulator. And again, that's where delta P programs on an ECM circulator are very helpful, that as zones start to close, you're not just going to like ram all that flow through the one zone, the one zone valve that's still open, and then maybe start to crack some of the other ones open. That can be a ghost flow scenario, just because the single speed pump with only one zone valve open is hitting a different duty point there, and is going to push those 7.5 C sub V valves open, is something that we've seen in the past too. Then what about the last kind of prevention method for ghost flow is a check valve. Do you want to talk about maybe like the difference between a spring check and a swing check too, if you're going to add one of those to a vertical stretch of pipe to prevent ghost flow?
Yeah, swing checks, I mean, at least in domestic applications, you want only in horizontal piping. But yeah, that spring check is good in horizontal or vertical piping. That will only open as there's enough force against it, and not just ambient temperature or a real low pressure differential pushing against it.
Yeah, so if you did have some, you may have a check valve right in the circulator. If you had a bunch of vertical lines going up, like if this was a huge buffer tank that was held at 140 degrees, you had no check valves going up to a bunch of radiant manifolds, you could have some two-directional flow, that if there's not a check valve, that the colder water in the manifold above starts to come down on the outside diameter of the pipe, and then the warmer water can drift up through the center. So you have two-directional flow. A check valve would fix that, would prevent that flow from happening, even if the circulator wasn't on. That one's going to take a little bit longer. That might be like overnight that some of those zones overheat, that the zone valve has been closed the whole time, but you had some ghost flow going back up through the other side. That would take a while, especially in a radiant example, but maybe a higher volume like steam, two-pipe steam retrofit, where you've got really big pipes and really big radiators up in the building, you could see a little bit more of an overshoot there, and that might be a good application to just press in a check valve there. But that takes us to the top of the hour, so I'm going to pause here. These all came from tech support conversations, so if you have something that we didn't cover today and you want to ask us more questions about it, this is the team that'll be answering the phone. If you give us a call, and we can go into a little bit more detail and figure out what the easiest path to kind of get back to the right balance would be. And then what I'll do is kind of cruise through a couple of the questions that we got, and we can do a couple of those. But if you do have to run because it's the top of the hour, thanks for joining us. So we talked about ghost flow as one of the questions. We talked about sizing. If you have like east and west DHW recirc and you want to use multiple circulators, that's fine too. And again, you just have to make sure that they gather to just a single circulator if you're doing it that way. Maybe it's less expensive to have a recirc pump for the east and west than one big one for the whole building, without getting into all the details for that. We had a question about balancing domestic water heaters. I don't know if this would be like a tankless or something like that, that balancing the two heaters to make sure that they're kind of getting equal run times there. There are a couple different ways to do that. That might be something that they can cascade differently with the controls to talk to each other. But if you had let's say two tankless water heaters next to each other in a mechanical room, and one of them had like 1 million hours of operation time and the one next to it only had like 50, you could balance your way out of that potentially with an automatic balancing valve. That could be a case that they're not truly like reverse return piping or something too. What else would come to mind with that if you saw that in a mechanical room, Matt?
Yeah, I mean, a lot of times I would not run into reverse return, run into that kind of Christmas tree piping, and it has to be right on the money, equidistant as you pipe those up, and just a little bit of a margin of error one way or the other, and one of those heaters is absolutely going to be favored over the other.
Yeah, and that if you had enough flow rate, that if it's oversized and they're built for redundancy, that might be something that you do like a lead lag that switches. But if you oversize the water heater and the path of least resistance is through one unit, you may never fire that second one, and that you know, just based on a difference of a couple GPM that would catch the first flow switch in the unit on the right before the one on the left or something. There was a question about NSF 61 and 372. So the thermosetter, the thermal balancing valve, has the NSF 61, which also gives you 372 basically. And then the automatic balancing valves have 372 only. So that's something to keep in mind depending on what your jurisdiction is. We get that NSF 61 seems to be popping up in more places, where from our standpoint, really the amount of lead difference in those two standards is so minimal that, like, I wouldn't say that it's a huge deal for us. But I completely get that NSF 61 also, you know, covers more things that are just different from the amount of weighted lead in a valve. So, but keep that in mind, that the thermal balancing valve, the thermosetter, would have the 61 compliance that could be useful. Okay, let's see if there are any other questions here that I should snag, or if we should follow up with them. There's a question about how closely spaced tees, how close do they need to be? So if this were closely spaced tees, 4 pipe diameters apart. So if you went with closely spaced tees instead of a hydro separator, the hydro separator is spaced perfectly. That's kind of, it's built with the exact dimensions and sizes that it's looking for with that 3-to-1 ratio. Closely spaced tees, 4 pipe diameters apart. So this is 1-inch pipe. Those 2 tees can only be 4 inches maximum apart. Otherwise, you're kind of drifting out of that that closely spaced tees. And then, yeah, there's a comment about for PEX repairs, if you can get the crimper in position, good luck. That can be where like a cold expansion with a compression ring type tool may be easier to get into that space too than getting your 1-inch old school crimper into a small space or something like that. Okay, I think that that's gonna probably be a good spot to pause here, and then I'll get back to any of the other questions that I missed today or tomorrow. So thank you, Matt. Thanks for being our guest expert today. Thanks for everyone for joining, and we will see you next month to talk about booster pumps. Thanks, everybody.
Thanks, everybody.